throw out the probabilistic when this integral does not converge for this kind of values. So, let's thank Roman again. So we remain on the imaginary side of extending the Liouville theory with the talk of Yiannis. But this time, if I'm not wrong, we have a more bootstrap approach.
Yes, that's right. That's right. Yeah. So thanks, Raul. Thanks very much.
The recording is going on. So I'll start again. So please, Yiannis, the scene is on you.
Great. Thanks very much for this very nice workshop and the opportunity to speak. And thanks to all brave of you who stayed up in the last talk of Monday's session. So yeah, I will be telling you a few things about the n=1 supersymmetric cousin of Liouville theory. And I will be referring, just like in the previous talk, to this time-like regime of the super conformal central charge, or imaginary. So whatever was imaginary in the previous talk, I will be referring to as time-like. It's some physics jargon that's not very much well motivated, but anyway, I will refer to it like this. But keep in mind that this is what was called before imaginary. And yes, indeed, as Raul said, I will be discussing the derivation of the three-point function of this theory from the side of the analytic conformal bootstrap. So this is a word of notice. My background is neither a probabilist nor a tensor categories or a VOAist. My background is analytic conformal bootstrap methods and CFTs. So I will be presenting things from this perspective. Okay. So just to make sure everyone is on the same page, the main objective of the conformal bootstrap is basically to try to find and classify all conformal field theories that obey some basic axioms. These axioms can be, as we all know, like from the associativity of the OPE to unitarity to locality and so on and so forth, respect of symmetry. In particular, in 2 dimensions, there is a very concrete notion of locality which goes by the name of generalized modular covariance. And this is a cartoon. I don't know if I have that. Okay, this is a cartoon of what I mean by generalized modular covariance of Euclidean correlation function to the CFT. So here, for example, let me take one example. This is a torus 2-point function of 2 primary operators. And this equality is supposed to mean that if I expand this correlation function into conformal blocks associated to quantization along this circle and this circle, this is supposed to give me the same result if I expand in a different base of conformal blocks associated to quantization along this circle and this circle. Of course, we are all familiar with the case of the sphere 4-point function, torus 1-point function. There's 2 cartoons here. And the point of the conformal bootstrap is to, without any reference to a Lagrangian or anything else, try to specify the set of conformal left and right conformal dimensions of primary operators along with their associated OPEs, the structure constants, that satisfy these relations. So this is the point of view that I'm taking here. There is no path integral, there is no Lagrangian, there is just a set of CFT data that satisfy these relations. So Liouville theory, I want to view it as a special example of these constraints. And okay, many things were introduced in the previous talk, so I don't need to say much. So I will be viewing, even though I wrote in the action here, I will be viewing Liouville theory as what is called usually in the physics jargon space-like Liouville theory, or Sigrid-25, as a particular solution to the bootstrap with central charge given by this usual parametrization that we all like. It consists of a continuum of scalar primary operators where H and H tilde are the same. And I've chosen this specific parametrization with a minus sign. So the spectrum of Liouville operators lives in this imaginary line. And the OBE coefficients are given by the celebrated DOCG formula. So this is the DOCG formula, which up to some normalization factor is basically given by this special function, this Barnes double gamma function, which is a meromorphic function with simple poles in this grid spanned by B and B inverse. So this theory, so all I gave you is a spectrum of scalars of conformal dimensions and some OBE coefficients. And the claim is that this is the unique scalar solution to the bootstrap equations for this B real part, or C greater than 25. And we can go into the arguments of this, but there's a very nice analytic argument, of course, by Jörg Dessner, and there are very good numerical analysis justifying the statement by these authors, and of course, many others. Of course, it has been mentioned a lot in this workshop that Liouville theory has very interesting connections in various fields of mathematical physics, from the AGT correspondence, quantization of moduli space of Riemann surfaces, of course, probability theory. There is sense that Liouville theory describes a universal sector of what is called irrational to the CFT. There is connection to 3D gravity, and so on. And of course, as we all know, there are various generalizations. You can add boundaries to the theory. We can consider higher spin generalization called total CFTs, and we can add supersymmetry. So this is what I would like to focus today. But before I do that, let me say a few words of what was discussed before as imaginary Liouville theory. I just have 2 slides on this. So timelike or imaginary Liouville theory is basically a solution to the bootstrap that holds if I plot the complex central charge plane in this C less than 1 region. And as was mentioned in the previous talk, there's a very good reason for it. If you blindly take the DOCG formula and analytically continue in this line, which corresponds to imaginary B, then you find that this formula diverges, exactly as was mentioned in the previous talk. So what you do is you go back and you ask for a different solution to the bootstrap equations. And this was done in these seminal papers, which basically written down this timelike or imaginary version of the DOCG. And so in terms of this bootstrappy philosophy, this timelike or imaginary Liouville theory is a non-unitary theory because the central charge can be negative. Here I call B hat the imaginary part of B. It was what is called theta in the previous talk. It still has a bounded spectrum, although the conformal dimensions exactly because of this imaginary B can be negative. The spectrum, let me skip this comment about the identity field. The spectrum consists again of some scalar primary operators with these conformal dimensions. And crucially, there is a different structure constant, which was what was dubbed imaginary DOCG in the previous talk. But here I would like to stress that there is a very interesting form of this timelike DOCG formula or imaginary DOCG formula. In particular, one can find a normalization of the vertex operators where the timelike DOCG formula can be written as the inverse of the DOCG formula, evaluated at this B hat, which is the imaginary part of my original B, and then rotated P variables. Okay, so I will come back to this. This is just a fact, which I think it's interesting. And by a seminal work by Sylvain Ribot and Raoul Santachiara in 2015, it was shown that actually numerical studies show that with this structure constant in this spectrum, the sphere 4-point function is crossing symmetric. However, I want to stress that there is still no analytic derivation of this fact. And there are many applications of this theory, some of them especially related to 2D percolation and conformal loop ensembles that were mentioned in the previous talk. There is some interesting connection with low dimensional models of DS quantum gravity and also low target string theories, time-dependent backgrounds, but okay, I don't know how many people interested in string theory here. So the goal of this talk is basically to provide the n=1 analog of this timelike or imaginary Liouville theory using the analytic superconformal bootstrap techniques. And in particular, we will describe the full spectrum of the theory in the so-called Neveu-Schwarz and Ramond sectors, and will provide explicit expressions for the structure constants. Now, the analog of C greater than 25, or what I call space-like Liouville theory, has been done in the past, and I will revisit it briefly. And if I have time, okay, along the way, I will mention some interesting properties of the shift relations that lead to these results. Great, so this is the plan. We'll start talking a little bit about space-like, and then we will go to the main result, which is the timelike n=1 Liouville CFT, and then I will end somewhere in future reactions. Any questions?
Why do you call this space-like and time-like?
Yeah, so this is physics jargon. It has to do basically with the sign of the kinetic term in the action. So you can argue that here, very briefly, where is it? So in the case of timelike, usually, and Roman I think mentioned it, usually phi gets rotated to I phi, and this gets an overall minus sign. So it's like a timelike, you know, it's like the sign of a timelike, like wrong sign kinetic term. So yeah, it doesn't have any physical meaning. Yeah, and also has some That's some background on this paper by Strominger and Takayanagi on this time dependence background string theory, but okay.
So
Yeah.
it's about the Dojita CFT correspondence or not?
Sorry?
Not ADS, but the Dojita CFT correspondence.
Dojita, sorry.
Dojita space, DS CFT correspondence.
DSCFT, yes. So this time dependent backgrounds, yeah, they relate to this.
I see. Thank you very much.
Okay, so let's start with this space-like version. So I will define what the space-like n equals 1 Liouville theory. So again, if you like an action, the action was written down first by Polakov in 81, when he was studying quantization of two-dimensional supergravity now. And the action basically consists of the linear dilaton plus a free fermion with this Yukawa-like interaction, and then again the exponential field, usual thing that we have also in n equals 0. And one can show that this action leads to a quantum theory that is characterized by n equals 1 super Virasoro algebra, which is an algebra spanned by the usual stress tensor and the supercurrent, which I call G of Z, with conformal dimensions 3.5, 0 and 0.3.5, the anti-holomorphic. And in terms of the modes, the algebra is given by this commutation and anti-commutation relations. CS here is the so-called superconformal central charge, which is given by 1 plus 2q squared. And famously, this algebra has a Z2 automorphism, which leads to the usual Navier-Schwarz and Ramon algebras, which basically amounts to the fact that the modes of the G are either half integers in S or integers for their mode. So what people refer to as space-like n equal 1 Liouville CFT is the theory defined for superconformal central charge greater than 9. This is supposed to be the analog of the central charge greater than 25 in the usual n equals 0 case. And the structural constants of this theory were bootstrapped right after, essentially a few years after the DOCC by Pogosyan and Raskov and Stasnikov. There was some reformulation by these authors also in 2007. So it is a unitary theory for these values of central charge and consists of a continuum of NS and Ramon primaries with conformal dimension given by this expression here. So in terms of the fields of the action, if you want to think about this, this vertex operator corresponding to the NS field is basically the exponential of phi. And in the Ramon sector, we have a double degeneracy, which is captured basically. So if you're familiar with the free fermion, this is like the spin and disorder operators. And then you dress it on top with this exponential of the field. And the formula for the conformal dimension of the Ramon field is just different by 1/16 exactly because of this guy. So the physical normalizable operators of the theory, they're characterized again by P imaginary, just like in the n equals 0 case, and the spectrum is bounded from below such. Now, what we want to do is to study correlation functions of these fields and determine the 3-point structural constants. So let's start with the NS sector. In fact, it turns out that the NS sector can be studied independently because it closes in its OPE. And notably, there are two independent structural constants. There are structural constants that enter in the OPE that captures the integer level descendants of the NS primary. And there is a different one acting, which characterizes the half integer level ones. So if I take the OPE of two NS fields, then there is one OPE coefficient, which I call CNS, with red here, which is exactly the coefficient sitting in front of the conformal family spanned by integer level descendants of this VE. Whereas C tilde NS, it's the one that, the coefficient that sits in front of the conformal family, which it's acting upon with G minus N over 2. These are half integer level descendants. And these are two different structural constants that we need to specify. So there are two DOCZ kind of functions that we need to find in the NS sector. So this is what I said. So this is, we have some 2-point function of NS field with some arbitrary normalization, 2-point normalization. We have this 3-point function of NS fields, which give me this CNS. And then this C tilde NS that I said it captures the conformal family with half integer descendants is captured by this. One defines this W field, which is G minus a half, G tilde minus a half. And the data that we need to specify in terms of the bootstrap is these functions. So all we need to know to compute correlation functions in the NS sector is this function for CS greater than 1. So Yeah, so in the Ramon sector, on the other hand, it doesn't, so we cannot just consider it separately, just like before, because of the form of the OBEs. And we have again some 2-point functions. This epsilon here plus or minus captures this double degeneracy that I mentioned before, some arbitrary 2-point function. And then we have 3-point functions of 2 Ramon fields with 1 NS field. And this semicolon here is supposed to capture that this P3 corresponds to a momentum that's associated with the NS field. So again, what we need to do is to find these functions. It is convenient in the literature sometimes to split this OBE coefficient associated with this 3-point function to C even plus or minus C odd, depending on which general guy you're talking about. So equivalently, we have to determine this C even and C odd. So how do we go about determining those? Well, the recipe is kind of old by now, and it's pioneered by Dessner, which basically is using 3 ideas. Use analyticity, the assumption of analyticity, the existence of degenerate representations, and crossing symmetry. So consider, for the 3-point function that you are interested in, consider an auxiliary 4-point function with an insertion of a degenerate guy, and consider crossing symmetry of this 4-point function. Now, because of the presence of degenerate fields, this correlation function here obeys a differential equation a la BPZ, which is a finite order differential equation with a finite number of independent solutions. So then if I expand this into conformal blocks in the 2 sides and use crossing symmetry, this leads to constraint equations of the CFT data, namely the OBE coefficients and the 2-point functions, which leads to these famous shift relations. So all we have to do is to look for solutions to these shift relations. This is exactly the same strategy, by the way, that one obtains the usual DOCC formula. So what we're going to find is we're going to find shift relations of these normalization independent bootstrap ratios, I call them, which is the OBE coefficient squared divided by the 2-point function in the NS sector, the one guy, and the C tilde, the other guy, divided again by the 2-point function, and similarly for the R sector. In particular, these shift relations, they take the form of ratios of these bootstrap ratios. In the numerator, the first ratio is shifted by B. In the denominator, the second ratio is shifted by minus B. And similarly, you have now 2 of these independent set of shift relations, one that only involves the C and one that involves C tilde and C. And on the right-hand side, we have some very explicit meromorphic functions of the momenta, P1, P2, P3, as well as of this parameter B that determines the central charge. And the latter is actually important in our quest to actually determine those constants for the timelike case. So just to give you a concrete example, what I mean, if you choose a convenient normalization for the 2-point function, then this previous shift relation that I wrote take this particular form here. So you see that these kappa and lambda functions, they are just ratios of gamma functions with arguments that depend on the PIs and the Bs. They are very explicit. So the question that we want to ask is what kind of functions solve these shift relations? So it turns out that in the n=1 case, remember previously for the DOCC formula, we have this Barnes double gamma function. Now for the n=1 case, we introduce 2 cousins of this, which is usually called gamma BNS and gamma B Ramons, which is just products of 2 usual gamma Bs. In the gamma BNS case, we have these particular arguments. So the first gamma B is x over 2, the second is x plus q over 2. Whereas the Ramon case, we have x plus b over 2 and x plus b inverse over 2. It turns out that with this function, we can solve these previous shift relations that I showed. Okay, there's a comment about the false of this, but essentially, we can see that these functions here, they solve exactly the shift relations that I flashed before. So these are exactly the analogs of the DOCC formula in the n=1 case and in the NS sector. And you can see that they depend on this gamma BNS and gamma B Ramon. Similarly, we do the same trick that I showed before, except now we involve some Ramon field. We implement the determinant representation, the Ramon algebra. And similarly, we arrive at these expressions for the C even and C odd. So this was very fast, I know, but I had 30 minutes. I have some comments. So it can be shown that this structure constant actually, there was papers after the derivation of this that show that both numerically and analytically, at least in the NS sector, they lead to crossing symmetric 4-point functions. The analytic part involves the fusion kernel. This is what I mean by analytic. You see here that the normalization that I chose does not depend actually on the cosmological constant. It's some kind of bootstrap motivated normalization. So these C's here, they all have, they all depend on the central charge and the piece. There is no mu. And there is, okay, just a minor comment. There's a well-defined limit when one of the external operators goes to the entity, then we recover the usual delta function structure for the 2-point function. Okay, so these are all I wanted to say about the space-like case or superconformal central charge greater than 9. Are there any questions before I go to the timelike case? So just like we said before, if we naively take the previous expression, try to analytically continue them in the superconformal central charge regime CS less than 1, then these formulas would diverge. And the reason simply is that these formulas that I wrote before, they again depend on this Barnes double gamma function, which also, as was mentioned in the previous talk, it depends on this, it has a natural boundary of analyticity exactly on this line. So we need to do something else exactly as in the n equals 0 case to figure out what are the structure constants in this regime on the central charge. So what we do is basically we go back to the shift relations and we look for new solutions valid exactly in this regime. So timelike or imaginary n equals 1 Liouville CFT is defined for central charge given by this formula. Here basically I just wrote B as IB hat. And I will put hat in all the quantities related to this timelike n equals 1 version. And to our surprise, it wasn't bootstrap at the full quantum level, except that there was some semi-classical analysis related to DS, etc. But it has never been done. It's a little bit messy because of the NS and the Ramon sector, but eventually it is doable. Again, just like the n equals 0 version is a non-unitary theory, which depends on a continuum of NS and Ramon primaries with these conformal dimensions. The physical operators of the theory are expected to lie again basically in the same locus as in the space-like n equals 1, except there is some important shift, which means that the spectrum is again bounded from below in the same fashion as before. So what we need to do is basically put hats on all the correlation functions that we had before. This is what I did here. I just put hats in the 2-point function, in the NS sector, in the 3-point function, the 2 structure constants, and then the Ramon sector. And all we got to do is to figure out these hatted functions. So again, how do we compute those? They are not simply the analytic continuations of the space-like ones that we said before. What we need to do is analytically continue instead the shift relations that led to those, and then look for new solutions to those. So in a nutshell, this is what we did, and this is a table of our results. So let me just say what this means. So again, the main point is that there are again inverse relations of the sort that I described in the very beginning for the n equals 0 case. So if I call CNS and CNS tilde, the 2 structure constants in the NS sector associated to the integer level descendant family and the half integer level descendant family, then the analogous quantities in the timelike case, they are given by the inverses of the opposite of the 2 in the space-like. So you see that this is the guy associated to the integer level descendants in the timelike theory, and is given by the inverse of the half integer space-like, appropriately rotated in the values of momenta and appropriately evaluated on this B hat parameter. Similar story for the other structure constant is the inverse of the other guy, and similarly for the Ramon sector, the analogous C hat even is 1 over C odd of the space-like. So just to be completely explicit, this is, for example, this guy here explicitly written in terms of this Barnes double gamma function or this gamma BNS and gamma B Ramon. So I don't have a very deep reason about this inversion, other than say that if you look at these shift relations that I talked before, if you go and analytically continue, which you're allowed to do in the B parameter, then they take an inverse kind of form. I have a slightly deeper reason than this, which originates from the fact that all these structure constants, also in the n equals 0 case, they arise as special instances of the fusion kernel. And the fusion kernel obeys something that is called Virasoro-Wick rotation symmetry, which we pointed out in this paper with Sylvain, 2023. But it's still not very much understandable. So I would like to get your feedback on this. If you have any idea, I would be interested to know.
In the case n equals 0, it's the same story, right?
Exactly, yes, yes. But yeah, other than technically, I don't have any other deeper reason why there's this inversion. Okay, so this is all I want to say. Let me end with some summary and future directions. So we provided explicit expression for the structure constant of n equals 1 Liouville theory in this imaginary or time-like regime of the superconformal central charts. Importantly, these are not the analytic continuations of the space-like ones, just like in the n equals 0 case. There is a sense that you can show that actually these are the unique solutions to the shift relations for B imaginary or B hat real. We can discuss about this, but basically it's the same argument that proves uniqueness of the imaginary de-Saussure formula. There is a very subtle issue in general in time-like Liouville theory, or also in the n equals 0 case, is that the identity limit does not reproduce of these structure constants, does not reproduce the delta function of the two-point functions. And we can discuss about this, but to put it shortly, like this can be attributed in a sense to the non-unitary nature of the theory. For some future directions, so now that we have this expression, it would be nice actually to establish crossing symmetry a la Ribot-Santa Chiara, maybe numerically, but also analytically to look for the associated fusion kernels, the n equals 1 fusion kernels in this case. In particular, this n equals 1 fusion kernels, just like the n equals 0 fusion kernel as we heard in the previous talks, is associated with UQSL2R. Now this the 6J symbol of some particular series of representation of UQSL2R. This n equals 1 fusion kernel this should be associated with the quantum deformation of the orthosymplectic algebra with 1 bosonic and 2 fermionic directions. I should mention that there's already some work about these connections by Somerus and Haddad collaborators, although to the extent that I know is not properly established, and I think there is still some work to do there. And in particular, since I'm not a probabilist, I would like to know what is the probability construction of n equals 1 Liouville theory, and whether this is an interesting problem for the probabilists in the audience. What is the analog of the Gaussian multiplicative chaos measure? Is this something interesting, or at least I don't know, I just raised the question. What is this inverse relation also of the structure constant? It's again something mysterious to bootstrappers or people who are in the CFT. Maybe someone has already a clue about this, but I don't. I would like to mention something that maybe rings a bell. There's something called the Van Dantzig problem in probability, which basically amounts to finding characteristic functions of some set if t is some random variables and f of t is some characteristic function of this, then there is a set of f's such that 1 over f of I times t is also a characteristic function. I don't know how much people are aware of this problem, but is a classification problem to try to find characteristic functions that also the inverse of them is a characteristic function, namely it obeys boundedness, positive definiteness, and so on. So this is the smartest comment that I can make about this inverse relation. Okay. And finally, to people who are interested in string theory, now that we have the structure constants of n equals 1 Liouville theory, we can try to build this non-critical string theory models with low deep targets, which is basically, on the world sheet, they couple time-like Liouville theory and space-like Liouville theory. Recently, there was this construction of the so-called Virasoro minimal string by these authors, which basically, on the world sheet, it couples time-like Liouville theory, usual n=0 time-like Liouville theory and space-like Liouville theory. And it was shown that has very many interesting properties, like there's a matrix dual of this string model, and the string amplitudes are very simple expressions of the external momenta and so on and so forth. So it would be nice to ask now, is there a fermionic extension of this model? Okay, that's all I have to say. Thanks very much for your attention.
There are questions?
So here you treated the case of imaginary or timelike and the standard case. Sylvain and Raoul, they constructed the theory for complex value of the central charge, at least the 3-point function by because the shift when you are not imaginary or real, they form parallelogram and up to elliptic functions. You can.
That's right.
So you can do this, and you can.
Indeed. There is again the similar, yeah, as you say, like when B is complex, then you have the freedom to multiply the structural constants that I showed with some elliptic function in the B and B inverse, and you again have solution to the shift relation. However, I think the point is that the only theory that will be crossing symmetric along the Liouville spectrum will be the one where this elliptic function is 1. This is a conjecture. I don't have a proof about this. This is my intuition from usual n=0 Liouville theory, although many people have.
So then if you take this special case, can you construct a supersymmetric with central charge that is complex?
Absolutely, yes. But I think if you go and test crossing symmetry, you will find that the spectrum that is eventually cross symmetric is the one that lies along the imaginary axis, with this multiplicative function being 1. We can discuss about this, but yeah. But in principle, yes. Solutions to the shift relations that will allow for this extra degrees of freedom, this extra multiplicative elliptic functions.
Can I make a comment?
Sure.
So about this inverse relation between the imaginary Liouville and the real Liouville, at least for the n=0 case, in probability, there is something called the mating trees, which can be used to understand the C smaller than 1 CFT coupled with C bigger than 25 Liouville.
Oh, I see.
And in that perspective, if the central charge add up to 26, you have some very nice structure.
That's right. Yeah, there is cancellation of the two because they are inverse. But I see.
This can be made the reverse, which is at least how we prove this imaginary DUDD for like percolation and so on.
I see. Okay. Thanks for this comment. Yeah, it would be nice to understand this better.
But then, what is the field that you would couple to supersymmetric stuff?
Yeah, I mean, for n=1, I have no idea. This is my first time knowing this n=1 things.
So yeah, no, it will be interesting. Yeah.
But do you have examples of where you have an idea? Maybe like say Toda, or can you couple Toda?
Okay, so at least I think from this talk, what I learned is that mating trees is not the only reason that the inverse relation holds. There should be some deeper algebraic reason behind this inverse relation, because maybe in this n=1 case, there's no counterpart of mating trees. And it would be nice to understand these mechanisms.
Sure. Yeah. That.
So
I definitely agree. Yeah.
For example, if someone can understand n=1 case, maybe there is also a way to understand Toda.
Maybe one comment is that all the structural constants that I presented, at least in the space-like case, there are particular instances of these crossing kernels. So, they're very, in particular, let me just mention the DOCC formula. The DOCC formula can be written as the analytic continuation of the fusion kernel to the identity. Where one of the you have pairwise identical operators for the external guys, and you have one of the internal guys analytically continue to the identity. And the work that I point out with Sylvain is we saw that these fusion kernels, they obey this Moore-Seiberg relation, like the pentagon identity, and this they admit some novel symmetry that we haven't, like we construct explicitly. And this symmetry basically takes the fusion kernel and inverts it. It gets from F to F inverse. So this is a special case of this more general inversion of the fusion kernel. But even at the level of the fusion kernel, I don't have a deeper explanation of why this inversion happens. So it might be equivalent statement to what I made before. Any other questions?
Okay, no more questions? Okay, so let's thank the speaker again. And maybe we'll close the lecture.
Yes, absolutely. Yeah, yeah. So